Let's look at an example, another example of a infinite series. Again, that just means we're adding up the terms of a sequence, an infinite amount of them, so we're never stopping our addition. It says determine whether the infinite geometric series. So what that's telling us is that this pattern here is geometric. They're telling us that. So let's see if we can figure out whether it's gonna converge. So let's start again by looking at the first partial sum. That's a 4. The second partial sum is 4 plus 4/3, which is 5 1/3. Now I'm going to use decimals here only because for the sake of the video it gets just as quicker later to write it as a decimal. So it's 5.3 repeating. The third partial sum is 4 plus 4/3 plus 4/9. 4 plus 4/3 plus 4/9. And that's 5.7 repeating. The fourth partial sum is that plus 4/27. And that's 5.925. Alright, the 925 is repeating. Alright, so we've done the fourth partial sum. So if you were to guess if this converges or diverges, what do you think? I mean, it looks like they're starting to get closer and closer to maybe 6. So I would guess maybe converges to 6. Right? If you take the list, right, 4, 5.3 repeating, 5.7 repeating, it looks like it's going to converge to the number 6. So I want to identify something here. I want to write this in sigma notation, and then we're going to refer to it. And you'll see why I'm doing this in a second. I want to write this in sigma notation. So we know that means using our sigma sign. We know that our rule for our geometric series is going to go right here in front. So the first term is a 4. So it's 4. And our R value, it looks like we're multiplying times 1/3 every time to get to the next number. So that's 1/3 to the n minus 1. There's our rule. And n is going from 1 to infinity. Okay, so hold this thought. We're gonna refer to this. Later. So consider what we had on the last page, right? We just had in sigma notation this infinite series, which looks like this. And again, that when you expand it out, you plug in 1. Your first term is a 4 plus 4/3 plus 4/9. Now that is an infinite series. We're adding up an infinite number of terms. But let's apply the formula we know, the finite geometric series formula. But let's just replace that n with an infinity and see kind of what happens. So s of infinity, right? If let's just say that n is infinity. This is a little bit abusive notation, but it's okay. S of infinity is our first term, which is a 4, times 1 minus, looks like my r is, well, I'm multiplying times 1/3 every time, so it's 1/3 to the infinity, right? Our n is infinity. And again, I'm referring to that formula there. And you divide that by 1 minus r. And so this is where you can really think about what's happening. According to the formula, what's going to happen to this 1/3 to the infinity? Remember, that means multiply 1/3 times 1/3 times 1/3. Do that an infinite number of times. Or imagine doing it an infinite number of times. What does that number start to go towards? You should see that it starts to go to 0, right? So the whole numerator starts to go to 4 times 1 minus 0. And that means that the numerator really just starts to go to 4 times a 1, right? 1 minus 0, divided by 1 minus 1/3. But that's just 4 divided by 2/3, or 4 times 3/2 times the reciprocal. And that's just 4 times 3 divided by 2, which is 6. And remember, that's what we kind of guessed. That's kind of what we guessed that sum was equal to. It looked like it was approaching 6. So the infinite sum looks like it's approaching 6. So this is a special this is special about what's special about geometric series is that we can actually find out what the series converges to if it converges. So how do we know, first of all, it's going to converge? If I give you a geometric series and ask you if it converges, the thing you ask yourself is, well, these numbers I'm adding have to be getting smaller, right? I mean, I started with a 4, then 4/3. They have to be getting smaller. Otherwise, if you keep adding numbers that are getting bigger, then of course you're going to just start approaching infinity. So those numbers have to be getting smaller. And why are they getting smaller? Well, they're getting smaller because that r is 1/3. That r is less than 1. So we need that r to be less than 1. I mean, take another example, a quick example. What if I gave you, this example, 4 plus 8 plus 16 plus 32. In this case, if I tried to apply that formula, if I wanted to add up all infinite terms of this series, well then my first term is a 4 times 1 minus my r is a 2, right? I'm multiplying times 2. 1 minus 2 to the infinity divided by 1 minus 2. This time, notice that that is not going to go to 0. That's going to go to a giant number. It's going to go to, it's going to go to infinity. 2 to the infinity is infinity. It's a really big number. So 1 minus that is a big negative number. So the point is, this formula would not work here, right? It's just going to give us infinity. And so that's the condition you need to check for an infinite geometric series. So an infinite geometric series converges only if the absolute value of your r is less than 1. So in our case, right, a third was less than 1. The reason it's absolute value is because your r can be negative. You can use negative r values there. If it does converge, so if it does pass this test, then we use the formula. And that is, it's the first term. So the answer is, I'm going to use this notation, the first term divided by 1 minus your r. Very easy formula. And again, that's all just a consequence of what happened right here. Alright, and so I'll do a few examples just so you can get some fluency with it, but hopefully you get a sense of, first of all, what we mean by converging, and also that we have a formula for a infinite geometric series only if your r value is a fraction less than 1.